Please welcome Brian Lauer.
Thank you so much. All right, well, thank you so much, everybody. Okay, so now prepare to color in the details. Again, this is my favorite talk. I love talking about Walt Brown. People call him today's Isaac Newton. He's just brilliant. And my goal is to get him the credit he deserves. And so Walt Brown, his background was, he went to West Point. He was an Army Ranger, paratrooper, went to MIT, got his PhD in mechanical engineering, sharp guy, taught at the Air Force College in Colorado. He ran the Benet Military Lab, which had 200 scientists, and dozens of them were PhDs. And he was the top dog. So he's a sharp guy. And he was going through South Dakota one time. And he heard on the radio that claimed they found Noah's Ark on a mountain. And, but going through, anybody ever drove through South Dakota? All you do is count the wall drug signs, right? Yeah? And so there's nothing to do. So he just started to kick it around in his head. Well, if they found an ark on a mountain, well, that would mean that the whole world was covered with water to get an ark up on a mountain. And if the whole world was covered with water, that means that a whole bunch of plants and animals got buried in mud and turned into fossils. And he said, wait a minute. If fossils are evidence for the flood, where's the evidence for evolution? And he started to ask his colleagues that question. What evidence do you got for evolution? And after 2 years of asking his very well-educated colleagues, he didn't have any evidence. And so he became a creationist. And then he came up with this theory. And I love, this is Bob Enyart on the right, Walt Brown's this way, Bob Enyart's that way. And Bob and them guys, they do radio interviews, and that's what colored in my perspective of the world. It was Walt Brown Week. Go into rsr.org, search Walt Brown, and he just explains it out there. It's like, oh, the world makes perfect sense now. And some of the things are very high on Google's lists, you can check that out. But these are the things. I mean, this book is a $30 book, brand new. It's out of print. How much do you think it's worth now? $100. That's the Walt Brown Week, the Hydroplate Theory. And this Jane Albright, we'll talk about her at the end. She critiques all the flood models. This is Brian Nichols' YouTube channel. And he talks, this is an all-encompassing theory. Talks about the origin of comets, the origin of radioactivity. If everything was very good, is it good to have uranium on the Earth? That could cause birth defects. So he explains, and we'll touch on it tonight, on how radioactivity could have been formed during the flood. And the neat thing is, I'm on the board at the Twin Cities Creation Science, so I get to help schedule the speakers. And I got Brian Nichol coming in next month. Well, actually, it's Zoom, so you guys can listen to this. Brian Nichol, go into tccsa.tc, and then you can ask for a link, and you're going to be able to hear him explain the origin of limestone. And so, yeah, I'm pretty excited about that. And you can see it on YouTube also, but if you zoom in live, you'll be able to ask questions. Okay, so here's the hydroplate theory. Now, keep in mind that theories typically go from effect to cause. There's cause and effect. We know what the effects are, and we're trying to figure out what caused them, right? So we know the effect, and we're trying to figure the cause, and we never really know because you can't go back in time to prove it. This is different. He sets up the cause with one assumption, just one assumption, and then lets the laws of physics go at it to give us the effects, and they match our world perfectly. And I gave this to a professor at St. Cloud State, because I know they don't have a theory for Grand Canyon. They got a bunch of theories, which means what? None of them work. And I said, you want to see a good theory for Grand Canyon? Check this one out. And she had this for about 6 months. We talked for about an hour and a half, and she said, the science works if the assumption is right. I just don't believe the assumption. So what I'm showing you works if the assumption is right. And he's just got one assumption. So what's the assumption? He assumes that half of the ocean was inside the Earth at one time. That's it. At least, and I'm saying at least half of the ocean was inside the Earth. So just think of the Earth as this big apple. And the skin is made of granite, 60 miles thick. There's a layer of water about a mile thick, and underneath that is basalt. That's it. That's the only assumption. So how do you get the laws of physics going at it? You throw in the moon, because the moon's going to tug on the Earth. High tide, low tide we got now. It's also going to tug on the crust. See, back then the Earth wasn't broken into plates like it is today. It was a solid crust. the crust. And so it'd get tugged and compressed, stretch and compress, stretch and compress twice a day. And now if I had a wire up here and I go back and forth, it's going to generate heat. Same thing with the crust. It got hotter and hotter and hotter and hotter. Heat had to go somewhere. It goes into the water. Water gets hotter and hotter and hotter. It wants to boil, but there's no room to boil. So it keeps getting hotter and hotter, and at 705 degrees, 3,200 psi, it becomes what's called supercritical water, where it's not really water and it's not really steam. It's just like these individual air packets all over the place. You know, it's not water, not steam, but whatever it is, it dissolves things like crazy. And it starts to dissolve the granite above and the basalt below, and starts to make these minerals inside that water. Starts making the limestone. You know, remember the carbon dioxide that got released? Well, it just got recycled into something else. And it makes quartz and salts and silica. You know, some of these are the cementing agents that we're going to need to cement sand into sandstone. So it just keeps making these elements and minerals in that supercritical water, and so there's sediment building up inside that chamber, and then eventually the chamber gets weaker and weaker and weaker. The pressure gets more and more and more. Walt Brown says he thinks, you know, under 60 miles of granite, can you imagine the pressure that's under there? He says it's 370,000 psi. Just tremendous pressure, hotter and hotter, more and more pressure. Eventually, the crust of the earth gets really weak, and it cracks. And the crack just rips around the earth at 3 miles per second, and so in 2 hours it goes all the way around the earth and then comes back together on itself. And people say, Brian, come on, if that happened, wouldn't it leave a mark? And I say, yeah, it did. It's called the mid-oceanic ridge. He thinks that it ended where that black circle is, because it kind of ends on itself, and then the water's just going to keep going. So if you run the movie backwards, he thinks it started up by Alaska. And then it just came right on through and just ripped apart, and the water's just gushing out like crazy. And so you're going to have 40 days and 40 nights of rain. You know, that's one of the things. It can't rain, so they say it can't, but this is how it could. You had a fountain of water coming up. And the Bible even talks about it in Genesis 7:11, I believe. For in the 600th year, in the second month, the 17th day of the month, the fountains of the great deep burst open. Something to that effect. And the windows of heaven were opened. So the water's gushing up with tremendous force. Okay, so now what do we have here? We got a lot of that sediment coming up onto the continents, right? And we also have two cliffs 60 miles high. On Earth, you can't get a cliff 5 miles high because it's going to crush the rock beneath. Here you got 2 cliffs 60 miles high crumbling into that supersonic water and just going flowing, and that's going out, and that's why the ratio is 65 parts granite, so you get the stuff on the side and the stuff underneath, and 35 parts basalt, which is just on the bottom. Okay, and it just keeps coming up and shooting up and shooting up, and eventually the sediment's going on top of the earth, which shows, this is how we get the continental sediments, that all the sediment's going on, and then it gets sorted, but that gives you are the layers of sediment. That's where the sediment came from. A lot of it came from inside those subterranean chambers, and liquefaction can sort it. So you got all this sediment, and you got these big waves because the continents aren't breaking up the tides anymore. And the moon's still tugging, so you can have these huge waves, and it could be 200-foot waves, 300-foot waves. There's a lot of weight on that sediment, and then it gets released, and then the water comes up, and then gets pushed down, and water comes up. Have you ever stood in the ocean? Anybody ever just stood there, and your feet start going deeper and deeper? Yeah, you're getting sorted. You'll just keep going, and that's kind of what's happening here. It could sort out those layers so they're pancakes. And so Bob Enyart told those geologists at ICR, just consider liquefaction as far how those layers got there. And it's really interesting. Grand Canyon has slanted layers covered by parallel layers. How does that happen? If those layers are millions of years, how do you just shave them off and put new layers on? Well, Brian Nichols' video talks about that. And what's really interesting in that red wall limestone, that red layer right there, that's 500 meters thick. So if you do the math, and you do it, it's supposed to be 50 million years. That's how long that layer of red wall limestone took. Okay, 500 million, and it's 500 feet. So 500 feet is going to be 6,000 inches. 500 million years divided by 6,000 inches, it's going to be 8,000 years per inch. Okay, it's going to take 8,000 years for an inch of that sediment to go rise, right? And you know what they find in it? Nautiloids. They're like a snow cone with a shrimp coming out. All right? And they're all pretty much in the same direction. And the thing that's real hard is 15% are vertical. And these are 18 inches long. So it's 18 inches times 8,000. It's supposed to stand vertical for all those years? No, I don't think so. I don't think so. So what else is happening? See, he doesn't think the Atlantic Ocean was there. He thinks that all eroded away. You know, Africa, and they tried to put that Pangea together, but it doesn't really fit. But if you left line it up with the mid-oceanic ridge and leave a few hundred miles for erosion, it fits pretty good. And what happens is it's eroding and eroding, so now there's going to be less pressure on the mantle. So now the mantle is going to start to bulges up, and the continent plate starts sliding. Like if you had a railroad track, you lift it up, the train's going to start rolling. That's what happened with the continents. So you got North America and South America sliding to the west. You got Africa and Europe sliding to the east, and they keep going until they meet resistance or run out of water, and then they buckle up and make the mountains. That's why the mountains are parallel to the mid-oceanic ridge. And they buckle up. It's kind of like pushing a carpet against the wall, or a car accident. It's going to buckle up the hood. And that's how the mountains rose up. And you notice that the Rockies are twice as wide as the Andes. And I think it's because it slid over the mid-oceanic ridge. And so you get now this is a compression event. These are getting pushed together like crazy. And it's going to make coal and oil and metamorphic rock, because marble is limestone plus 600 degrees plus pressure. Diamonds are carbon plus 600 degrees plus pressure. And that pressure, extreme pressure and heat, they carbon date those, and they find carbon. So they have to be less than how old? 103,000, right? Doc rock. And then these are folded mountains in British Columbia. How do you get rock to bend? It had to be pliable at the time they got pushed together. And you can do this experiment at home, but I'd ask your parents, to see if you can ask to bend their favorite piece of china. Is that going to bend? No, it's going to break. And this is interesting. Oh yeah, Dan's got a rock. I was going to pass it around this time. But I think he's got a rock that has granite, and then it's filled in with white stuff. And I think the white stuff is quartz. And this is Gunnison Canyon in Colorado. And it got crushed together, and quartz is made of, the first thing that's going to melt in granite is quartz. And I'm thinking there's tremendous pressure, it cracked, and then that granite melted and filled in those cracks. And he's got a perfect rock. Go on the table on the corner and ask him to see this round rock, and it's crushed granite glued together with white stuff, the way it looks. And I think that's what happened here. And it's very difficult to get that white stuff intruded into that, the sides, especially the thin stuff. And the interesting thing about that type of rock formation, it's at the bottom of the Grand Canyon. That's the basement rock for the Grand Canyon. So that rock got crushed too. It's the Vishnu's schist. And then you got the rock, the mountains that slid to the side. You got the mid-oceanic ridge. And that's how you get a mountain range, by stretching it in two directions. It's bulging up. You zoom in on them, those are the tension cracks. There's pressure coming up from underneath, stretching the rock, and then when it finally stretches, it cracks, and then it releases the pressure. So these mountains are being formed by stretching it in two directions. It doesn't make sense from any other perspective. And then how do you get the plateaus next to the mountains? Because the mountains are a big mass on a small base. Big mass sinks in. Well, if something's sinking in, something's got to rise up. And that's how you got the plateaus rising up there. So it's hydraulics. What's the force? Hydraulics. Gravity is pulling the mountains down, and the hydraulic force is pushing the plateaus up. Okay? And it breaks them off on piecemeal. It doesn't push it all up at once. It piecemeal pushes it up like that. And so then you're going to might have some lava flow going up in those cracks. And if there's a big flood that comes through and it's going to try and wash all that away, it's going to hit the top, hard stuff on top, that lava flow, and it's going to flow around it. And guess what we got? Red Butte, Montana. So there's 1,000 feet of sediment above the Grand Canyon that got washed away before they could start carving the Grand Canyon. And notice where it is. It's right down near the Grand Canyon. And it's very, very interesting. I think this is this is key to putting together the puzzle. Okay, so now if the mid-oceanic ridge is rising up everywhere, similarly, something's got to sink in. What sinks in? The Pacific Ocean. That's why it's the ring of fire. It just got sucked in, a lot of pressure, a lot of heat, a lot of melted stuff. So that's where the lava, magma comes from. And that's how you got the Mariana Trench, almost 7 miles deep in the Pacific. That's why the trenches are in the Pacific. And it's just so much different in the Pacific. There's even a continent that sunk in. It's called Zealandia. Have anybody ever heard of that? About the size of India. They found evidence that land-based fossils there. So that's sunk in, and that was a prediction of Walt Brown too. You're going to find granite inside the Pacific Ocean. And that's what they found. Okay, so now the origin of the continental shelves. How come we got that slope? You know, you got the continents, and then it slopes, and then it drops off. Why does it slope? Well, just think of it as a fire hose or something. You know, just think of this as a hose. The water just doesn't come up all at once. The water, I mean, there's 60 miles of granite slamming down, and then the pressure is building up, so it releases and shoots up again. So this thing, they call it fluttering, keeps slamming down. So it's going to wear the nozzle of the end of the granite off more than the rest, and that's how it got tapered. Okay, and that's how you got the canyons in the continental shelf. Walt Brown says the continents were higher, and they've sunk in. So the continents were higher, the water gushed off, cut the canyons, the continents sunk down, and then filled it up with water. And then you got Red Butte there. We'll take a quick overview of Grand Canyon. How'd that little river cut the canyon? It wasn't little at one time. And look at this funnel-shaped object. That's the key to the Grand Canyon. You see that funnel? It's 12 miles wide. Those cliffs are 2,000 feet high. All that 2,000 feet had to get washed away to start cutting the canyon. And what was happening, and the plateau's rising, so you got two huge lakes, Grand Lake and Hopi Lake. If you would dam up Grand Canyon, you'd get some big lakes. And at roughly the size of Grand Canyon, or the Great Lakes, plus all the sediment in the soil at the time too. Okay, so you got this mile-high lake ready to breach. What's going to happen when all that potential energy starts flowing over, going down? It's going to start washing away the sediment until it hits something hard, the Kaibab limestone, and then it spreads out. It didn't cut into the Kaibab limestone, it spread out and made that funnel. And then it starts to undercut Hopi Lake, and Hopi Lake's even higher, so you get more water gushing down, and that's what's washing away the stuff by Red Butte. Just all that stuff's getting wiped away, and that's what's left. Anybody ever been to Niagara Falls? Imagine something 20 times higher with 1,000 times the water flow. That's what he thinks what's coming out of those lakes. And water can do a lot of damage. This is the Guadalupe River in Texas. They got 30 inches of rain in a week, and it went over a spillway, and it cut a canyon 1 mile long, over 50 yards deep, and hundreds of yards wide through solid limestone rock. Water can do some really damaging stuff. It's been happened in 24 hours. Okay, and there was boulders the size of mobile homes were ripped up from the earth and mostly dry now. And so you got these big boulders banging down on the bottom of the riverbed, and just tremendous damage. And it almost happened with the Glen Canyon back in 1983. It almost went over, so they had water going through the spillway. You see that man right there? All that water is just gushing out of there. And then there's dirt started coming out, concrete coming, rebar just started coming out. The dam was starting to shake. They turned it down. And what happened? They had this thing called cavitation, where if there's a bounce or air bubble in that fast flow, it's like dynamite just blowing things up. And it made inside that steel reinforced concrete, it made a hole 32 feet deep, 40 feet wide, and 150 feet long. And so now they've realized we got to put air tubes in there to keep it from cavitating. And they figured out where to do that so that doesn't happen anymore. Anybody ever been to Mount St. Helens? Okay. Yeah. So you had it doesn't take millions of years to cut a canyon. You know, the mud flow blocked up Spirit Lake, and then in one day they saw it happened. You know, it cut a canyon, 1,000 feet wide, 140 feet deep, in 9 hours. That was a mud flow. Catastrophic. They call it the mini Grand Canyon. And then there's an engineer's canyon on the right. Okay, and that brings us to Petrified Forest. Anybody ever been there? In Arizona? Why is that at the bottom of Hopi Lake? You know, Walt Brown says that there was a lot of silica in that water. And when the water cooled off, that solution cooled off, it had to get out of the solution, so it went into the logs. And that's what petrified the logs. That's why it's at the bottom of that lake. Yeah, Jerry was saying, yeah, you can make it real quickly. Petrified wood. This one says you can make it in a laboratory rapidly by adding silica into it. And then Monument Valley, again, at the bottom of another lake, because that's what it is. It is at the bottom of a lake. There's 1,400 feet of sandstone underneath it now, but at the time of the flood, when the lake was there, it was just sand. 1,400 feet of sand, and the lake drains off, so the sand in the water rises up and starts to erode things. And you know, if there's something blocking, it's going to go around the sides. And that's how the mesas, buttes, and spires formed. This is the bottom of a lake. And so how do you get a canyon under 2 kilometers of ice for Greenland? Well, the water flowed off, and then the ice age came and filled it up. Same way with the lakes for our Antarctica. And what's interesting about Antarctica, they find 91 new volcanoes beneath Antarctica's ice. So when they're freaking out about the ice melting, blaming it on climate change, it's like, no, there's volcanoes underneath there. Yeah, that's another talk. But how did the ice age come? Only the evolutionists can't explain it. So what is an ice age? So let's define it. It snows more than it melts year after year after year. That's an ice age. And so how do you get it to snow more? Well, it needs to be warmer. You need more precipitation. If it's too cold, it can't carry the moisture. It has to be warmer winters. But how do you get cooler summers? Well, that's because during the fall, the continents were higher at that time, plus a lot of volcanoes were going off, so there's a lot more aerosols in the atmosphere blocking the Earth's sun. So you got warmer winters, cooler summers, and 400 or 500 years of that, you're going to get the ice age. So why isn't there an ice age in Alaska or Siberia? Because it came down as rain. It was close enough to the ocean where it got the moderating effect from the ocean. It came down as rain, and then it went farther inland, and it became ice. And in 1815, Mount Krakatoa, that went off, and just one volcano. It lowered the temperature of the Earth so much that in northeastern America, they had snowstorms in June. And the ice formed in lakes in July, just from one volcano. So how does the ice age get, once it starts evolutionary-wise, once you start reflecting more and more of that heat away, it should never end. How come it ended here? Well, in those 400 or 500 years, the oceans are starting to cool off, so we're starting to get cooler winters, plus the atmosphere is starting to clear up, so you're getting more sun's heat. So it took 400 or 500 years to build it, a couple hundred years of that, and we're still, to a certain extent, recovering from the ice age. Okay, and I give a talk on that. There's a book on my table called Inconvenient Facts by Wrightstone. Everybody should read that because it destroys that climate change alarmism. He says freaking out over CO2 right now is like worrying about your gas tank overflowing when it's an eighth full. We've had 8 times more carbon dioxide in the past. And then he points out, hey, carbon dioxide is not pollution, it's plant food. More CO2 means more food. Less droughts, because they don't have to have their openings open so much to get the carbon dioxide they need, which dries out the plant and dries out the soil. If we had more carbon dioxide, and there's co2science.org or .com, you can see how much more wheat we'd get, how much more rice we'd get, how much more food we get. But you know what? The more solar farms we have, less food we have, less housing we have. So anyhow, moving on to the mammoths. Keep in mind, they're not Arctic animals. It's not wool, it's hair. And they don't have an oil gland to keep it waterproof. And they eat too much, 300 pounds a day, and they drink too much, 30 to 60 gallons a day. There's not enough food in the Arctic for them. They're temperate animals, where there's lots of food and lots of water. So how do you freeze something that fast while it's still standing up? How did it get so cold so fast? That's cold hail. Big cold hail. How did we get cold hail? Because some of the stuff was shooting up with such tremendous force, it went out of our atmosphere. Went up into outer space, got super cold, and came slamming down on the mammoths and buried them. And you know what's frozen carbon dioxide? Dry ice. and just buried them by I don't know how many hundreds of feet, maybe, I don't know, but they're frozen to the ground. And so he predicts you're never going to find oil under the mammoths. You're never going to find layers of marine fossil under the mammoths. He thinks that's the bottom of the flood. Okay, and so we'll see what happens there. And Bob Enyarts goes a step further. It's like, well, they could have got washed somewhere. You know, that's a possibility. But he says you'll never find it under a standing mammoth. So it'll be interesting to see what happens. Okay, so that's how you froze them. How come they didn't thaw out? That brings us to the big roll. Okay, the northern hemisphere mountains and the southern hemisphere mountains pretty much cancel each other out, except for the Himalayas. Nothing in the southern hemisphere cancels out the Himalayas. So if you were to have a spinning top or bowling ball, put some extra weight on it, there's the weight on top, it's going to the side. It's bringing the top to the side, so therefore the side had to go to the top. So what happened was the mammoths were living in a temperate environment. The Himalayas was formed more towards the Arctic, and I think it moved 3,000 miles to the south. So you got mammoths getting fat and sassy in Mammothville, and then the Himalayas come up and they moved them up to Mammoth Chill. So they never thawed out. And similarly, it brought up the redwood trees, it brought up the shrews and the badgers, and brought up all that stuff to the top. It brought tropical palm tree down to the bottom in Antarctica. That's how you get these weird things that couldn't normally live there where they're at right now. Okay, and so what happened in the Earth, when the Earth was rolling like that, the Earth is not round. There's a bulge at the equator. So as it's rolling, it's putting a lot of stress on that bulge, and that bulge cracks. That's how you got the 90 East Ridge. 3,000-mile crack pointed directly, you guessed it, at the Himalayas. And so that's how the 90 East Ridge was formed. And there it is. I love getting globes of what's on the bottom. At the bottom tells a big story. So is that why the moon doesn't, is that why the equator's different? I don't know.